There are several factors that must be considered in studying gas absorption equipment, three of which are the heat effects, absorption of multi-component systems, and absorption with a chemical reaction. These factors may guide a chemical engineer in designing the appropriate gas absorption equipment and may provide information on how to deal with such systems. Heat effects in gas absorption. In some absorption processes, especially if it involves a chemical reaction, heat is liberated or absorbed. Usually, it is liberation of heat which accompanies an increase in temperature of the liquid solvent. There are various heat effects that can be considered. One is the heat of solution of the solute. It involves the heat liberated in mixing, heat liberated in condensation, as well as heat liberated in reaction. Others include the heat of vaporization or condensation of the solvent, temperature difference that may result to heat transfer between the solute and the solvent, and loss of heat to the surroundings. For plate columns, a heat balance may be performed over each plate and the resulting temperature determined. For adiabatic operation, where there is no removal of heat from the system, the temperature of the streams leaving the absorber will be higher than those entering due to the heat of solution. This rise in temperature lowers the solubility of the solute gas, so that a large value of the liquid-to-gas ratio and a large number of trays will be required than for isothermal operation. For pack towers, the rise in temperature affects the graph of the equilibrium curve. Differential equations, as well as balances in mass and heat, must be integrated numerically. Sometimes, for simplicity, it is assumed that the heat is taken up by the liquid while there is no temperature rise in the gas. This overestimates the liquid temperature, which will give a taller tower than necessary. It is very difficult to arrange a cooling system for pack towers. Sometimes it is necessary to remove the liquid from the tower at certain intervals and cool it externally. The figure shows the effect of temperature on the equilibrium curve of ammonia in water. It can be seen that the slope is much steeper in the curve with the higher temperature than that of the lower temperature. There are examples of well-known systems that release heat in considerable amounts. In these systems, the heat evolved cannot be neglected since they are too large. These examples include the absorption of ammonia in water, the dehumidification of air with concentrated hydrochloric acid, the absorption of carbon dioxide in amine solutions and sodium hydroxide solutions. If the amount of heat released is very large, it may be necessary to cool the liquid. This is most conveniently done in a plate cold room, either with heat exchangers connected between consecutive plates or with cooling coils on the plate. The overall heat transfer coefficient between the gas-liquid dispersion on the tray and the cooling medium in the tubes is dependent upon the gas velocity, but is usually in the range 500 to 2000 watt per square meter Kelvin. There are several approaches in which heat effects may be dealt with depending on specifications. One example may be to add internal or external heat exchanger to remove heat from the absorbers. Others are treating the process as isothermal, then adding a safety factor, employing the adiabatic model, in which assumptions are the heat of solution manifests only as sensible heat in the liquid phase, and solvent vaporization is negligible. Using semi-theoretical shortcut methods derived from rigorous methods, and using rigorous design procedures using a computer. A classical isothermal method assumes that the temperature in all points of the tower is equal to the inlet liquid temperature all throughout. It is most useful if the feed gas is sufficiently dilute. It usually tends to underestimate the required depth of packing by a factor of 1.5 to 2, so safety factors must be added to the design. The classical adiabatic model assumes that the heat of solution serves only to heat up the liquid stream and that there is no vaporization of solvent. This assumption makes it feasible to relate increases in the liquid phase temperature to the solute concentration X by a simple enthalpy balance. The equilibrium curve can then be adjusted to account for the corresponding temperature rise on an XY diagram. The adjusted equilibrium curve will become more concave upward as the concentration increases, tending to decrease the driving forces near the bottom of the tower. This method also requires a safety design factor. However, if vaporization of the solvent is assumed, cooling might undergo, which offsets a part of the temperature rise that would have been predicted if no vaporization takes place, giving a prediction of a lower tower height. Absorption in multi-component systems. When there are no chemical reactions involved, absorption of more than one component from an insoluble gas depends on temperature, pressure, and the liquid-to-gas ratio. The liquid-to-gas ratio is normally determined by the volatility or the physical solubility of the least soluble component. The more volatile the component of the gas, the less soluble it is, because of the tendency to escape into the gas phase. When the condition of saturation exists, the value of y sub 1 over y sub 2 will remain finite even for an infinite number of plates or transfer units. If the amount of volatile component from the incoming fresh solvent is negligible, then the limiting value of y sub 1 over y sub 2 for each of the highly volatile component is y sub 2 over y sub 1 is equal to s over s minus 1, which is equation 14-50 of Perry's 8th edition, where s is equal to the mass times the reciprocal of the liquid-to-gas ratio of m, and the subscripts 1 and 2 refer to the bottom and top of the tower respectively. If the gas is dilute, absorption is treated separately for each component as if other components are absent. If the gas is concentrated, the change in gas and liquid flow rate as well as heat effects must be considered. Trial and error calculations from one theoretical stage to the next is required for accurate results. There are two design methods dealing with multi-component systems as stated by Perry: by graphical method or by algebraic method. For an example of the graphical method, figure 14-9 of Perry's 8th edition shows the diagram for the complete absorption of pentane and heavier components from a lean gas mixture. The oil used as solvent for this case was assumed to be solute-free, and that the key component, butane, was identified as that component absorbed in appreciable amounts, whose equilibrium line is most nearly parallel to the operating lines. 4 theoretical plates have been stepped off for the key component butane on the figure, and are sufficient to give a 75% recovery of butane. The operating lines for the other components were drawn in with the same slope and were placed so as to give the same number of theoretical plates insofar as possible. The diagram of 14-9 shows that for the light components, equilibrium is achieved easily in fewer than 4 theoretical plates, and that for the heavier components, nearly complete recovery is obtained in 4 theoretical plates. The diagram also shows that the absorption of the light components takes place in the upper part of the tower, and absorption of the heavier components takes place in the lower section of the tower. The algebraic design method uses the Kremser formula in describing multi-component systems. The left-hand side of the equation represents the efficiency of absorption of any one component of the feed gas mixture. If the solvent oil is stripped off of solute so that x sub 2 is equal to 0, the left-hand side is equal to the fractional absorption of the component from the rich feed gas. When the number of theoretical plates n and the liquid and gas rates have been fixed, the fractional absorption of each component may be computed directly, and the operating lines need not be placed by trial and error, as in the graphical approach described earlier. Absorption with chemical reactions. There are a number of processes in which a gas reacts chemically with an absorbing liquid. Some examples are the absorption of carbon dioxide in caustic soda and absorption of carbon dioxide in ethanolamine solution. Mass transfer is made much more complicated. The absorption process proceeds as an irreversible reaction wherein A plus B produces AB, where A is the solute gas, B is the absorbing liquid, and AB are the products of reaction. As the gas approaches the liquid interface, it dissolves and reacts at once with B. The new product AB, thus formed, diffuses toward the main body of the liquid. The concentration of B at the interface drops, which causes the diffusion of B from the bulk of the liquid phase to the interface. The chemical reaction is rapid and B is removed very quickly, so it is necessary for the gas A to diffuse through part of the liquid film before getting to B. There is thus a reaction zone between A and B which moves away from the gas-liquid interface, taking up some position towards the bulk of the liquid. The final position of this reaction zone will be such that the rate of diffusion of A from the gas-liquid interface is equal to the rate of diffusion of B from the main body of the liquid. Figure 12.10 in Richardson and Coulson's Chemical Engineering 5th edition says that when this condition has been reached, the concentrations of A, B, and AB may be indicated as shown. In this figure, the plane of the interface between gas and liquid is shown by U, the reaction zone by R, and the outer boundary of liquid film by S. Then A diffuses through the gas film as a result of the driving force PAG to PAI, and diffuses to the reaction zone as a result of the driving force CAI in the liquid phase. The component B diffuses from the main body of the liquid to the reaction zone under a driving force Q, and the non-volatile product AB diffuses back to the main bulk of the liquid under a driving force M to N. The differences between an absorption process with a chemical reaction and an absorption process without a chemical reaction is shown in the figure. In designing gas absorption towers, it is difficult to determine the size of the tower for absorption with a chemical reaction. A laboratory scale experiment must be carried at all times. Some studies report insufficient data on how to proceed the process. Some report that their equipment was unsatisfactory. Some did not predict that their process were of 2 stages, and among others. Data from specific designs are however limited on applicability. Risk is high whenever extrapolation over their data and their conditions is done when applying on a full-scale plan.